Hi friends, in this video, today we are going to discuss about Gauss Divergence Theorem. So we will just see qualitatively what does it mean, what is Gauss Divergence Theorem, what it gives you, the mathematical expression, and then the physical significance of Gauss Divergence Theorem. So before starting this Gauss Divergence Theorem in detail, like its statement and the mathematical expression, let us just revisit to what we have already done in one of the videos. I have already discussed this. We have discussed something like divergence of a vector field, divergence of a vector field, okay, in terms of integral, okay, in the form of integration, okay, in integral form, integral form. So I'm going to use this, okay, this concept again, divergence of a vector field in integral form, to define or to show you what is Gauss divergence theorem. So if you remember, divergence of a vector field, we said when the del operator or nabla operator is operated on the vector field with a dot product, with a dot product over here, right, with a dot product, then we said divergence, right? And in the integral form we wrote it, okay, we wrote it as limit del v tends to 0 and closed integration of the vector field over an elementary surface area, that is ds. ds is very small, and divided by del v. So this ds is actually what? Ds is a closed surface, okay, that encloses a volume. So that encloses a volume. So here it's a closed integration over the surface. That means the surface area is a closed one which encloses the volume, right? So this is what we wrote. We interpreted mathematically what is divergence of a vector field in integral form. Okay, what does it mean? We have already discussed in one of the videos. You can revisit, you can see. So divergence of a vector field actually gives you what? The net flux emerging per unit volume. Okay, the net flux emerging per unit volume. That is what we said. Now, what is this net flux emerging per unit volume? Here you can easily see it gives you what? This is actually the net flux emerging per unit volume, right? So net flux you can see is a dot ds integrated over the whole surface, right? When the surface is a closed one, it will enclose the volume. So per unit volume, when the volume tends to 0, that is infinitesimally small, you can just revisit that, that video, divergence of a vector field, then again you can see actually what was the meaning. So this is how we actually defined um, uh, you know divergence of a vector field, and in the form of integration we wrote it, right? Now I will use this concept to write Gauss divergence theorem. Gauss divergence theorem is nothing but the extension of this physical significance of divergence of a vector field, or from the integral form you can just write what is Gauss divergence theorem, right? So this can be written as, if you'll see here, we have del dot a, and here it gives you del v, that is the infinitesimally small volume del v. Okay, if you remember, we considered, in that divergence, when we discussed divergence of a vector field, I considered a parallelopipe, and the dimensions of the parallelopipe were considered to be infinitesimally small. In along x-axis we consider dx, along y-axis we consider dy, and along z-axis we consider dz. So the volume was considered to be dx, dy, dz, right? So dx, dy, dz was considered to be dv. So dx, dy, dz are infinitesimally small, so your volume considered over here is very small, or you can say this dv is very small. So which is actually represented here, you can see in the form of a limit, right? So here if you will see this limit del v tends to 0, del v, that is nothing but your dv, or a infinitesimal small volume, right? And here you got the a dot ds factor here, a dot ds integrated over the whole surface. That gives you what? The variation of the vector field along that closed surface, right? So that's why we said the net flux coming out of it, a dot ds gives you the net flux coming out of it, right? So here we can just write it, rewrite it as, this is simple, we can rewrite it as integration over the whole volume. Okay, and then del dot a, which we got here this side, del dot a. Okay, and then this limit del v tends to 0 and del v can be written as dv. Okay, the elementary volume that we considered can now be written as, this limit won't be there, and you got the closed integration over the surface, and then the variation of the vector field over that closed surface ds, a dot ds, right? So this is what is your Gauss divergence theorem. Now this mathematical expression that we wrote for Gauss divergence theorem, which is nothing but another interpretation of the divergence of a vector field in integral form, right, or in the form of integration, right? Okay, now what does it mean actually, what it gives us? If you will see, you can see this del dot a dv. Okay, del dot a dv, volume integration of divergence of a vector field. Can you see this? Integration over the volume dv, that is the volume integration. So volume integration of what? Volume integration of divergence of the vector field. So divergence of the vector field, we took. Okay, and this is exactly equal to what? The surface integration of what? The vector field over a closed area, over the closed surface, over a closed area. So here we equated actually what? We got a relationship between the surface integration, okay, of a closed area which actually encloses a volume. Okay, so if I will say, this integration over as, that means this is a closed surface area. Okay, and that will enclose a volume, that will give you a volume, some volume value, right? So this is how they are related, right? So simply if you want to write the statement, you can say, um, this vector integral theorem, actually this is a vector integral theorem, okay, which relates volume integral with surface integral. That is what I said. So volume integral with surface integral, okay, this is how they are related. Okay, and you can say the volume integral of divergence, the volume integral of divergence of a vector field, okay, over a given volume, okay, over a given volume, is equal to the surface integral of the vector, surface integral of the vector over a closed area, over a closed area. The surface area is closed, we said. Okay, so over a closed area enclosing the volume. So this closed area must enclose this volume, right? Then you can write this particular mathematical statement, right? So I'm just rewriting it again, what we got. So what we got here, what is that integral theorem? Actually, this gives you integration over the volume of what? Divergence of a vector field, right, is equal to surface integral, closed surface integral of the vector field A dot ds. This is how you can actually relate volume integration with surface integration. When we will do numericals based on this, you will have clearer idea, better idea on this. Okay, so this is what is your Gauss divergence theorem. And on the statement, as I said, I can just rewrite this. Okay, the same thing what we wrote mathematically, but you need to express it, write it in words as well. So I will write the volume integral of, the volume integral of divergence. We took divergence over here, del dot a is divergence. So divergence of a vector field, which is, we consider a here, vector field which is a here, right, over a given volume, this volume, over a given volume, okay, is equal to the surface integral, is equal to the surface integral here. Okay, closed surface, you can see, integral of the vector, the same vector a, vector, okay, over a closed area. You can see this closed integration. So closed area, so this closed area actually encloses the volume. So closed area enclosing the volume and closing the volume. Okay, so this is the statement we can write for Gauss divergence theorem, and this is your mathematical expression that is that we can use to actually convert, to write the volume integration in the form of surface integration, or surface integration in the form of volume integration. So this is simple, and just remember that if you don't just remember this, at least you can write the meaning of divergence. From that you can get it. What we said, divergence is nothing but net flux per unit volume, and net flux means what? We just wrote it as A dot ds, net flux. Okay, and if you want to convert, relate surface integration to volume integration, we know that a closed surface area will enclose some volume. So this divided by del v, and this del v is infinitesimally small, so use the limit, that limit del v tends to 0, right? Then you take this del dot a over here, and this del v, limit del v tends to 0, and this thing will be your dv. So you write this as del dot a, okay, dv integration over the volume must be equal to whatever is left over here, a dot ds, right? So that gives you a dot ds, closed integration, surface integration. So I hope you understood this. um, Thank you for watching.